Hello, welcome to this lesson in engineering mechanics, statics. In this batch of lessons, we'll be moving our discussion along in the concept of vectors and how to use them, and talking about forces and all of the different operations that we use in engineering mechanics relating to that. And at this point, I expect that you have already viewed Engineering Mechanics Volume 1, where we've talked about the fundamentals of vectors, coordinate angles, magnitude, unit vectors. All of that stuff is incredibly essential. We're going to be taking all of those concepts and building on them one step at a time. So everything in this course is absolutely fundamental material that everyone taking a class in engineering mechanics and statics is going to need to master. Now, in this lesson, we're going to be talking about what we call force directed along a line. And that is exactly what it sounds like. If I tie a rope to the ceiling and I anchor it to the ceiling and I'm holding that rope and I'm pulling on it, okay, then I'm going to be pulling with some force, and that force is going to be directed in a direction that's governed by that line. So you're going to see as you work engineering mechanics problems that this is going to be something you see all the time. You'll have support structure over here, you'll have some ropes, some cables, a pulley maybe, and all of these force vectors are going to be oriented along the line of the rope or the line of the cable or whatever. So we're going to talk about how to write that down. Now I want you to recall something that we've talked about before. Recall that any vector, this is kind of review, recall that any vector A can be written as an x component of A in the I direction or the x direction, plus some y component of A in the j direction, which is a unit vector in the y direction, plus some z component of A in the k direction. And this is stuff that we've covered many times before. You should be very comfortable. X, y, z is a three-dimensional representation of any vector. All right, now if we want to draw this, you should probably get pretty good at drawing these sorts of three-dimensional things. I always draw kind of it looks like x, y, but really it's going to be z, and this will be y here. So you take out of the board, you represent that as a slanted line. If you stare at that long enough, it kind of looks like it's a three-dimensional thing. And the way that you label it is this will be x, this will be y, and always pointing up is z. And if you forget which one's x and y, you just take the right-hand rule. You take x, curl it into y. Your thumb should always point to z. So if you had this backwards, made this x and y, curled x into y, your thumb would be pointing the wrong way. So it's always x, y, and z. That's how I remember it. All right, and basically any vector A can be represented in three dimensions by an arrow that starts, usually we talk about starting at the origin. So this will be what we're talking about here, vector A. And we've learned before, I'll try to change colors and make it a little bit easier for you to see. If you kind of take the tip of this arrow A and kind of take a dotted line down here, down in there, and then if you go and do something like this, parallel to the y-axis, and then this parallel to the x-axis. Of course, my arrow's not quite long enough, so I'll fix that real quick just to kind of basically trying to create the illusion that this is a three-dimensional thing. And then to really complete it, it really helps if you draw yourself a little dashed line like this. So if you stare at this long enough, this should pop out of the board and look like it's an arrow. It's got a z component, an x, and a y, and it's kind of sitting there in three-dimensional space. And this guy is supposed to be kind of the projection, if you were looking down, what it would look like in the x, y plane. All right, so anyway, every vector can be written like this. And so we know from experience that notice this is the x direction, so I'll write it over here, that the x component that we're talking about is really this distance here. The y component that we're talking about is really this distance here, because we're going from the origin out. Notice how it's three-dimensional, so this distance here would be the y component. And then the z component is how far above this plane it is. So again, I'm drawing on a flat board. It's not perfect, okay? So you have to visualize three-dimensional space. And in reality, you're gonna have x, and then you're gonna have y, and you're gonna have z going up. So x and y are perpendicular, z is perpendicular to those guys, and you have some point in three-dimensional space and an arrow connecting it to the origin like that. So basically, to get to any point, you have an x component, a y component. Those are in the xy plane down there, and then the z component comes up out of the plane. That's what we're trying to draw right here. So basically, to formulate any vector, you're going to start at the origin, you're going to walk along x, this many units, you're going to walk along y, this many units, and you're going to go out of the plane of that up z units. And that is how we formulate a three-dimensional vector. But notice that this vector is starting at the origin and it's going out to a point. And that's how we always introduce this stuff, because it's the easiest way to show you, hey, a vector is an arrow, it points someplace. Here's how you formulate the direction it points. And of course, the length of the vector is going to tell you the magnitude or the strength of that vector, whatever it is you're talking about. All right? But all vectors don't have to start at the origin. For instance, I'm in a room right now, so the origin might be in the corner over there, where I have x, y, and z coming out from the corner like that. So I could put my force vectors from the corner, but again, what if I have that rope anchored to the ceiling, and I'm pulling on it? Well, one end of the rope is not at the origin, and my hands certainly are not at the origin if the origin is really in the corner. So when I pull here, I do have a vector, but it's not anchored to the origin in this scenario, and that's how most of the problems are going to be in mechanics. There. So we want to figure out how to create something, or how to write something down called a position vector. It's just a vector, just like any other vector you might have, but it's not anchored at the origin because, as I mentioned, you might have ropes or something and there might be tied all over the place. So how do you draw something like that? Well, to simplify it, I'll just do it in 2 dimensions first. So this is the x direction, and now we're switching a little bit. This is the y direction. Because we're looking at top down. This is a 2-dimensional view, so just pretend you're hovering over, you're looking down. Z is coming out of the board, right-hand rule, x going into y, z is coming out of the board. We're just doing this to make it a little bit easier. So again, what if I had a vector that did not start at the origin? Maybe it started at point A here, and maybe the vector ends at point B over here, so we would say it goes from A to B like this, all right? Again, neither one of these endpoints are actually at the origin, but we know that the coordinates of the A point is xa, ya. It's just the coordinates of this point. This guy is xb, yb. Okay? And we say that this vector is the r vector. Typically in physics, science, engineering, the r vector, r bar, is typically a position vector. It's pointing from point A to point B. Now, in all the vectors we talked about so far, or at least a lot of them, the starting point is just the origin, and the ending point is the tip of the vector. And that's the simplest way to introduce vectors. But in general, you don't have to start at the origin. You might have ropes hanging all over the place where their starting points are in different locations. In each case, you have a starting and an ending location that each have a set of coordinates, x and y. That's all I'm trying to say right here. So then if you write all that stuff down, then this position vector r can be very simply written as xb minus xa in the I direction, and I'll tell you what this means in a second. And then you have yb minus ya in the j direction. All right, what does this mean? Okay, what it's saying is that the vector r has an x component and a y component. You should see that because it's sitting in an xy plane. This vector has some x component here. Some x component would be horizontal. It also has some y component, which is vertical. The x component of the vector here is just simply the difference between the starting point and the ending point, xb minus xa. It's basically telling you what is the distance here, xb minus xa. That is how far the arrow points in the x direction. In the y direction, it's the similar thing. The yb minus ya is just giving you the vertical component of this vector. So it looks complicated, but all you're doing here is you're saying, okay, any vector in general can be written from a starting point to an ending point, and the x component of the vector will be the difference in the x components, and the y component of the vector will be the difference in the y components. Okay? So you can say, you can start walking from A to B. So in this case, the way I have it here, xb minus xa, I'm assuming that A is the starting point, B is the ending point, because vectors have direction, remember, it's an arrow. It's not just a line segment. So whenever I write it as xb minus xa, I'm implying that B is the tip of the arrow and A is the origin. B is the tip of the arrow, A is the origin. That's kind of important because as you get into actual problems, you'll need to write your vectors down and you'll be assuming, okay, the vector's pointing this way, so it's going to be ending point minus starting point. Ending point minus starting point, ending point minus starting point. Now we'll do some real problems, of course, but this is just kind of a general idea. In 2 dimensions, you write a position vector here. Also notice that in this case, if A, the starting point, actually was at the origin, like if the arrow started here and just continued up to point B, then x sub A would be 0, right? And y sub A would also be 0. So if we actually did have the vector start at the origin, this would be 0 and this would be 0. So it would reduce to how you normally write vectors. Some component in the x direction here, and then some component in the y direction. You would still, in other words, if it starts at the origin, you're still doing the subtraction, you're just subtracting 0. So it's not in contradiction with anything we've learned so far. So let's move on down the line, and let's say this was a position vector in 2 dimensions. Let's look at a position vector in 3 dimensions. It's really exactly the same thing, but I like to ease into things sometimes. So let's draw our nice 3-dimensional system that we should be pretty comfortable with. You have x, y, and z. X always goes here, y always goes here, z goes here. Remember, you can curl x into y, and you'll get z. So in the previous time when I mentioned it, I said, hey, the vector starts at the origin and it ends over here. And that's all true in that case when the vector starts at the origin. But for position vector, the vector may start someplace different. So let's change colors. Much as we've done before, the vector might start here at point A, and it might end over here at point B. So I'm going to draw this. Now, so far it looks very similar to what we've done before, because I'm drawing on a 2-dimensional board, but you've got to remember this is 3-dimensional. So to try to show that to you, let's do our best. So this, you can draw yourself a little dotted line down here, and then you can draw yourself a slanted dotted line, and then over here, and then over here. When you draw 3 dimensions, the secret is when you project down, you need to follow the parallel lines of your axes, and that makes it look 3-dimensional. So now you can see that point A is above the xy plane, and it's kind of over toward you out of the plane of the board. And then point B, okay, I can draw it going straight down, let's say to about right there. And then I can draw myself a dotted line over there. And I'm going to follow the angle of the x-axis like this, follow the angle of the y-axis over there. And I really should have chosen a different color for that, to be honest with you. And actually shouldn't probably go all the way like this, just to keep the illusion. Probably should just go like that. So if you use your imagination, you can kind of see it. I probably should have used a different color for the B position, but you can kind of see point A is up above and toward you. Point B is up above the plane and away from you into the board. So this is now a 3-dimensional vector, which is kind of pointing into the board and of course up as well. So this is a general vector, R, in 3 dimensions. So if in 2 dimensions, the x component is just the subtraction of the x components and the y component is just the subtraction of the y components, how do you think a vector will be written in general in 3 dimensions? It was very, very similar. In general, the x component is xb minus xa in the I direction, plus yb minus ya in the j direction, plus zb minus za in the k direction, which is the z direction. So basically, this is a position vector in 3 dimensions. You're just subtracting the x components to give you how much the arrow points in x. You're subtracting the y components of these points to find out how much it points in y. And you're subtracting the difference in the z components to figure out how much the arrow is pointing up. And each one of these forms a component that we have talked about before. So again, if A happens to be at the origin, like we've been drawing all up until now, so the vector points here, then all of the A points would just be 0, and you're just subtracting 0, and so it's the same as we've been doing before. So this is all building up to something, right? I've been telling you, hey, we're studying force along a line. So the example I'm giving you is I have a rope anchored to the ceiling and I'm pulling on it. So I'm pulling with 5 newtons or 10 newtons, and I'm pulling in a specific direction. The direction is now governed by this, because if I have an anchor in the ceiling with a rope, I know, and let's say that the origin down here is in the corner, x, y, and z, then I know the components or the coordinates of the anchor point. I know the coordinates of my hand. That forms a line segment, and from this I can figure out a position vector in 3 dimensions, right? So I can actually figure out the direction that that force is pointing just by using this equation here if I know the components of everything, right? But how do I find the force vector? How do I roll it into the fact that I'm pulling at 200 newtons. How do I write that as a vector? I know I'm pulling, and this is giving the kind of the direction. How do I put those two components or two concepts together so that I can write that force vector along that line in 3 dimensions? That's what we're going to do on this last little board here. So let me write this down. Force directed along a line. And that's basically what I'm going to show you here. So notice that we have an R vector here, which I have defined. That is the length and a direction of vector R. What if I want to find a unit vector in the R direction? We've talked about unit vectors a lot, and we said you can find a unit vector direction in any direction that you want. If you have a vector pointing a certain direction and you would like to find a unit vector in that direction, it's just pointing the same direction, but it has a length of 1. We're going to need that in a minute, and I'll show you why in a minute. But for now, this is something we've learned before. A unit vector pointing in the R direction is just simply the R vector that I've created divided by the magnitude of the length of R. So if I create this vector here and I have 3i plus 2j plus 5k, after I do the subtractions I have an actual vector, then all I have to do is I take that vector and I divide by its length. And I can find the length from the Pythagorean theorem. We've done that many times before in volume 1. And once I do that, I'm going to get a unit vector. It will point in the same direction as R, but it will only have a length of 1. Okay? Then, finally, the punchline to everything we're doing, then the force directed along this line, defined by the unit vector here, is going to be equal to the magnitude of the force I'm pulling with, like 100 newtons or whatever, times the unit vector in that direction. So that's how you combine them. This is what it is right here. The unit vector in the direction I'm pulling is specifying only the direction, and it only has a length of 1. So I multiply that by, if I'm pulling with 100 newtons, I multiply that by 100, and then that gives me a force vector pointed in that proper direction, okay, in that direction. And so since it's the force, magnitude of the force times the unit vector, that's exactly the same thing as the magnitude of the force. Remember, the unit vector is just this. It's the position vector divided by its magnitude. So this is how you would actually calculate it. And then if I wanted to spell it out even in more of its glory, I would say that this is also equal to the following, and this will look a little bit ugly, but I promise you it will make sense. The magnitude of the force that I'm pulling with times, and this is going to look a little bit big, but bear with me, xb minus xa in the I direction, plus yb minus ya in the j direction, plus zb minus za in the k direction. And I'm going to divide this entire enormous thing by something else that's enormous. It's going to look very scary, but I promise it's not going to be scary. You have xb minus xa squared plus yb minus ya squared plus zb minus za squared, like this. All of this I'm going to circle because this is the kind of stuff you're going to see in your textbook. Eventually you're going to get mechanics that's going to talk about vectors, it'll talk about forces, and then it'll be force directed along a line. And you will eventually come to a page which has a very ugly looking equation like this. I want to teach you not to memorize equations, I want to teach you what the equations mean so you understand what they mean, right? Basically what's happening is, if you cover this up, this is the position vector R. Okay, these xb minus xa, that's just the difference in the endpoint and the start point giving you the position vector directed in some direction. Okay, when you divide that by the square root of these subtractions squared, this is just the x component of this vector squared, the y component of this vector squared, the z component of this vector squared. When you take the square root, that's how you find the length of a vector, right? That's basically the Pythagorean theorem in 3 dimensions. We've done that many times. So this vector divided by its magnitude just gives us a unit vector in the direction of that I'm looking. It gives me the same directional components, but with a length 1. And when I take that and multiply by whatever I'm pulling with, 100 newtons or 150 newtons, then this is basically going to get multiplied to all the components that you end up with, and you're going to get your force vector. So this force vector will have an x component of the force, a y component of the force, and a z component of the force, which will be specified in the ijk, xyz component. So this will become a lot clearer in the next section when we do an actual problem. So I don't want to talk too much about it now, but just consider for me that basically if I'm pulling on a rope with 100 newtons, like if it's anchored into the ceiling over there, clearly there's going to be an X component of my force on that I'm pulling. There's going to be a Y component of my force because I'm pulling at some angle, and there'll be a Z component of that force. When you do this calculation, that's the vector you get, the X component of the force, the Y component of the force, the Z component of the force. And the way you get it is you pull with how many newtons, and then you have a unit vector which points in the direction that's governed by the anchor point and my starting point. So that's basically what it boils down to. It'll become a lot clearer in the next section. We'll work a problem, and we will show you how to deal with force directed along a line, and you'll find out how common it is in mechanics. So let's go on into the next section, and we'll work some problems, and I promise you it will become very, very simple how you deal with this in mechanics.